Is the audience mostly grad students?
Yes, but some people are from outside as well. So yeah, some I can recognize from the names, but some I cannot. So let's wait for a few more minutes, Haeyoung, if that's okay with you. Yeah.
Yep. I guess I should turn off my video for the
Yeah. Okay, so maybe we'll start the seminar. Thank you very much for joining this fourth seminar from the ITS seminar series on smart infrastructure. This is hosted by Center for Smart Infrastructure and Berkeley Engineering and Berkeley ITS. And it is my pleasure to have Professor Noh from Stanford University today. Professor Haeyoung Noh is an associate professor in the Department of Civil and Environmental Engineering at Stanford University. Her research focuses on indirect sensing and physics-guided data analytics to enable low-cost, non-intrusive monitoring of cyber, physical, human systems. She's particularly interested in developing structure to be self, user, and surrounding aware to improve users' quality of life and provide safety and sustainable built environment. And you'll see a lot of exciting things from today. Some of the results you'll see from here for her lecture today have been deployed in a number of real-world applications, from terrains to Amish community and elderly care centers to pig farms. Professor Noh, before joining Stanford, she was a faculty member at Carnegie Mellon University, and she received her PhD and MS degrees in civil and environmental engineering and the second MS degree in electrical engineering at Stanford University. Her BS degree was in mechanical and aerospace engineering at Cornell University. And she received many awards, including Google Faculty Research Awards twice, 2013 and 2016, and the Dean's Early Career Fellowship and the NSF Career Award. So a lot of awards. So Haeyoung, thank you very much for joining, agreeing to give this the talk today. And I'll pass the floor to you.
Thank you for the introduction, Kenji. So let me share my screen. Is it working?
Yes, it is working.
Okay, great.
Thanks.
Thanks. Okay, good afternoon, everyone. So this is Haeyoung Noh. So today I will introduce the concept called structures as sensors. And this concept together with the physics-guided learning to indirectly monitor humans and surroundings using structural vibrations. So let me get started. So these days, our daily life heavily depends on various civil infrastructure systems like buildings and bridges and various transportation systems. And we are actually continuously physically interacting with these infrastructure systems. So we started thinking, what if we can make these structures smarter? Like by making the structure be aware of themselves, we can prevent some catastrophic failures and reduce accidents. But by better understanding the occupants inside these structures, we can provide personalized services, enhance healthcare, security, and even reduce the environmental impacts from these humans and the structural systems. And then to achieve this goal, the first step we thought we need to do is to collect data about these structural systems. So we will put sensors on the bridges and rails and also inside the buildings like cameras, vibration sensors, environmental sensors, just like this. We can put a lot of sensors in these structures to collect information about them. However, we realized that sensing in the infrastructure system is not a trivial task. There's a lot of challenge involved with it. First reason being that many of these structures are very large in scale, very complex, which makes the monitoring system quite expensive because you need to put a lot of large-scale sensing system inside. And then, moreover, we found that the sensor lifetime is quite short. This is a relative measure because when we think about what's a typical lifespan of a building or bridge that we build, it's usually about 50 years to 100 years. If you go to some countries, you see some of the structures are standing there for 1,000 years or even more. So, but then on the other hand, what would be the lifetime of sensors that are used for monitoring? Often, like an easy example will be, think about how often you change your cell phone. So probably a couple years, or if you're really good, maybe 5 years. And I've seen some people saying 10 years. But then you see the order of magnitude there. So the sensor lifetime is a lot shorter compared to the expected lifetime of the infrastructure systems or the structural systems. That means we need to have frequent updating of this monitoring system itself, which will make the sensors even more expensive. And many of the events that we want to detect tend to be a little complicated. So we need to often collect many different types of information, meaning we will need many different types of sensors, which will make the monitoring system even more expensive. So to address some of these challenges, our group has been working on answering the first research question shown here. How can we sense everything, a lot of information, in a more maintainable and sustainable way? And to answer this question, we developed the concept called structures as sensors. So what does it mean? Now, let me explain this concept using an example. So here's an example of a sensor, microphone, that senses sound. So typically, traditionally, what we mean by the physical component of a sensor is there's a small diaphragm inside the microphone that will vibrate when the sound wave comes in. And that vibration is transferred to the electrical signal. So that's how we sense the sound using microphone. And now we expand that idea and we'll think of the entire building structure or entire bridge structure as a physical component of a sensor. So the entire structure becomes the sensing medium. So when we have these structures like a building or vehicle structure, vehicle frames, their vibration responses are dependent on the structural characteristics of themselves. Depending on what's the stiffness, what's the mass of the structure, their vibration characteristics is determined. But in addition to that, we found that their responses are also impacted by the human users inside. Like if people are walking around, there's a dance class, there's gonna be some vibration induced. So even in the car, if you're moving around, it will introduce some structural responses to the vehicle frame. And then also different environmental conditions will, of course, impact how these structures respond or vibrate. So we will collect all these different information through the structural vibration, which will be extracted using the data acquisition system. And then we extract features out of those raw data, which will be put into the learning module. And this learning module will infer the different sensing target informations, like what kind of human activity is happening in this structure, what's the structural health state, and any interesting surround events like traffic condition or construction happening around the building and so on. So this is the structures as sensors approach, the problem solved. Okay. But then there's never free lunch. Life is not easy. We found that to enable the structures as sensors approach, we actually need to collect a lot of data. And that's because these structural responses contains a lot of different information. So there's multiple sources of excitation inducing the structural vibration, which is a good thing because there's a lot of information in there, but it's also challenging because if you want to extract only the desired information out of the structural vibrations, you have to be able to understand all these different sources so you can just separate them and get only the desired information out of this mixture of information. So we need to collect a lot of data to make it possible. And then we also know that every structure is unique. If you go out in the city, you see there's different buildings standing there, every single structure, and they look a little different. And even if they're designed exactly same, they're gonna be constructed in a different way and utilized in a different way or sitting in a different climate zone. So over the time, the structure becomes own unique structure. Each structure becomes unique. So in order to understand every single structures and their characteristics in a different way, so we need to collect even more data. And finally, a lot of interesting events that we want to detect, like if there's any damage happening to the structure, or if there's any health hazard or some intruders coming in for security issues. Then all these events are more rarely occurring events in the normal lifetime. So in order to have enough samples of those rare events, we actually need to have seriously large amount of data. So now it seems like to make the structures as sensors approach work, we just need to go and collect a lot of data. Simple solution. But then again, getting real world data is actually very, very difficult and expensive. Here's an example. This photo on top shows one of the railway bridges that we monitored. The students here are putting sensors on the railroad. What we did was we collected the vibration response of this bridge when the trains were not running, because we were only allowed to get onto this bridge between 1 a.m. and 6 a.m. because that's when the train stop operation. So we got there, put the sensors out there, and then have this train drive back and forth to create different traffic conditions. And we also wanted to create different damage scenario, but it's a real operational bridge, so we're not allowed to induce real damage. So in order to change the structural conditions, we drove out a couple other trains and parked them on different parts of the bridge to change the load distribution within the bridge. So we went out at 1 a.m. We drove a couple trains there, drove it back and forth and collected data. And we spent the whole weekend to 3 days working on data collection. And at the end, we're left with 20 samples of each damage case. We created 3 damage cases. 20 samples, that's it. A whole weekend spent with me and a couple other grad students. So you see, it can be quite time consuming if we want to, imagine if we want to collect the data from a damaged bridge 1,000 different times, enough to run some data-driven approaches in all different environmental conditions, like different temperature conditions or traffic conditions for different damage severity, damage location, and damage type, and so on. It's going to take a lot of time to collect that information. How about asking a person to walk around in a building 1,000 different times, wearing different shoes, walking in different speed, and so on? And what if that person's your grandma? You definitely don't want to ask your grandma to do that experiment. So we concluded that this high dimensional problem with small data or data scarcity is a fundamental challenge that we need to address when we try to use machine learning or data-driven approach in the real world structures. So in addition to the first research question about how can we sense, we been working on answering the second question on how can we understand the output of the structures as sensors with minimal data requirement. And to answer this question, we developed a physics-guided learning approach. So how does it work? In addition to the structures as sensors approach that I showed earlier, we include the structural response modeling, which will describe how the wave disperses or how the wave propagates inside the building or bridges or any structural systems, and also how the sensing targets behaves, like what's a typical human behavior patterns, how does the environmental property changes over time, and so on. And all these different components from features to structural response model to sensing target models will be informed by physical knowledge or domain knowledge. And all these different models are combined through the physics-guided learning, which will be used to infer the sensing target information. And then the sensing target information will be fed back into the data acquisition system to update the sensing configuration to optimize the data collection, as well as fed back into our structural system to enhance the performance of the structures in terms of structural health, as well as better serving the occupants and making less environmental impacts. So to show how this physics-guided learning approach with the structures as sensors idea works, I'm going to show some of the ongoing projects in our group. And the first example involves using the vehicle frame as the structure, as vehicle frame structure as a sensor. And that's to do the Driveby bridge health monitoring. So maintaining bridge is very critical to make sure that the bridge is safe and reliable. But then the current practice to maintain bridges heavily depends on human inspection. Like human inspectors, engineers go out to the field and visually inspect if there's any damage happening. They may use some tools on site to assess whether there's any critical damage happening. So you can imagine it can be quite labor intensive, costly, time consuming, and it could be subjective because there's a human decision in there. So to address some of these challenges, researchers have developed various structural health monitoring systems to directly monitor the infrastructure states. Like you go ahead and put the sensors on the bridge to directly collect the bridge responses, or on the bottom right hand side photo, I have a dedicated car or truck instrumented with very expensive equipment that can precisely measure the status of the bridge structure. So this car will be slowly driving across the bridge to measure if there's any defects or damage happening in the bridge. But then, given that there are more than 500,000 bridges in this nation and the scale of this infrastructure, this is very expensive to both install and maintain this monitoring system themselves. So to this end, my group has been working on developing a new solution called the Driveby Bridge Health Monitoring System, which uses the vehicles as sensors. The regular operation of vehicles that will just regularly travel across these bridges, we can diagnose damage on the roads and bridges using only the onboard sensing system that's in these vehicles that's driving at a regular traffic speed. So here's an example. So you see the visualization here. There's a bridge and the car. These vehicles are carrying the sensors, vibration sensors inside. And as the vehicle crosses the bridge will vibrate, which will be transferred into the vehicle vibration. So we are sensing the bridge response indirectly through the vehicle vibration responses. So this is a scalable solution because single car can go drive around multiple bridges to monitor them. And there's no on-site installation or maintenance required, so a lot lower cost in terms of instrumentation. And most importantly, there's no traffic interference happening while this monitoring is being done. But then there's never free lunch. We found some challenges associated with this approach. So as I mentioned, there's a single car that will be driving across multiple bridges, collecting multiple bridges vibration responses. But then different bridges will have distinct structural characteristics, which leads to different data distribution, even if these bridges are in the same damaged state. That means when we develop a model, when we go ahead and collect the data, responses of the bridges, and also the corresponding damage label for that particular bridge and develop a model to assess the damage, that model is hard to generalize to other bridges. So that means we need to go ahead and collect this labeled data or damage labels for every single bridge that we want to monitor and build a separate model for each bridge, which seems quite impractical. So here's a simple visualization to show what's actually happening. So I have red circle representing damage at support location from bridge 1, and blue circle representing damage at a different location, let's say midspan in bridge 1. And once we collect these data and the corresponding damage state, in this case, damage location, we can go ahead and build a classification model to classify where this damage is happening. But then when we move on to the next bridge, bridge number 2, and collect the same set of data for these two different damage states, the previous decision boundary, the previous classifier, is no longer effective for classifying damage for bridge number 2. So what are we going to do? Are we going to go ahead and collect a new set of data and then build a different model? So that can be done, but that means a lot of time and effort needed to collect data and build a model for every single bridge. So instead, we came up with a solution where we're going to transfer these features into a new space where the features coming from or the data coming from the same damage state will be overlapping on top of each other. And therefore, these two data sets can share the same decision boundaries or same classifier. So this approach is called the unsupervised domain adaptation, which transfer the features from one space to a new space so that the feature is informative to different damage labels, but they are invariant across different bridges. So let me show you how the method actually works. So I'll show you an architecture. So once you collect the data from source domain here, which is bridge 1, and bridge 2, which I will call a target domain that I don't have a labeled data for. These data are sent into the feature extractor to extract the feature. And for source domain data or bridge 1 data that I have both the sensor data as well as the corresponding damage label, it will be sent to the location predictor network to classify what damage state this data belongs to. Okay. So this is actually a typical framework on how the data-driven approach will work to build a classifier based on the one bridge's data. But then in addition to this, which will be in charge of extracting feature that's task informative, meaning it can classify the different damage location very well, we attach something called the domain classifier, which will try to decide whether the feature extracted is coming from bridge number 1 or bridge number 2. And of course, I mentioned that we want these features to be overlapping on top of each other, meaning it should be very difficult to distinguish whether the data is coming from bridge number 1 or bridge number 2. So that's what's called the adversarial learning, meaning we are simultaneously training the damage predictor classifier and the domain classifier. But in terms of the performance, we want to extract a feature that will maximize the damage predictor, while that will minimize the accuracy of the domain classifier. So the feature can be task informative. It is very good at classifying what damage state it is, but it's terrible at estimating which bridge the data is coming from. Okay? So it's ensuring task informativeness and the domain invariance. So it looks like the problem solved. Then we found the second challenge. So often in practice, bridge monitoring has multiple tasks that we need to achieve at the same time. For example, we need to first detect whether there's damage or not. Then we need to decide where that damage is located. And then we need to quantify the severity of the damage. So that means there's going to be multiple data distribution shifting at the same time when we move from one bridge to another bridge. Here's an example. So in addition to the circles, which indicated different damage locations, now we have squares. So all the squares are indicating severe damage state, whereas circles indicate the minor or mild damage state. And again, the red color means damage location at the support, and blue markers represent damage location at the midspan. So based on the data distribution, we can put them into the classifier and come up with the two decision boundaries. But if we move ahead, go ahead and collect the data from bridge number 2 and plot them on the same space, you see that these features are not having very different distributions. So we're gonna apply the solution from the first part and project this feature to a new feature space, such that the features belonging to the same class will be overlapping on top of each other, so that now they can share the same damage, same decision boundaries. So this is basically just simply combining the unsupervised domain adaptation method that I introduced before with the multitask learning. Multitask learning is basically trying to simultaneously learn multiple tasks at the same time. So it's extracting the feature that contains the shared information of damage location and damage severity. So the advantage of this simultaneously learning method compared to more naive sequential learning, so basically doing one unsupervised domain adaptation to solve the damage location problem, and then move ahead and have another second unsupervised domain adaptation method to solve the damage severity problem. So that will be a more naive sequential approach. But then that has the danger or risk of error propagation, meaning if you make a wrong decision in the first task, that error will propagate and you'll make a very poor decision for the second task. So by doing simultaneous learning, we reduce the risk of error propagation. So the architecture-wise, it's a very simple addition. So in addition to the original or previous architecture we have, we just attach another classifier that's for the damage severity classification. Okay. So it looks like this will solve the problem of multiple bridges and multiple tasks. Then it wasn't that easy. So we ran into the third challenge, that simply combining the domain adaptation method with the multitask learning actually has a problem, because every task has a different level of difficulty. Meaning, like in our case, localization was an easier task than quantification, because if we go ahead, go out and collect the data, bridge response data for different damage locations, we found out that the data distribution is pretty far apart from each other when it's a different damage location. Whereas for the given location, if the severity of the damage changes, it was a gradual, slow migration of the data distribution from the low level of damage to the severe level of damage. So the separability of different damage state was separability was a lot higher for localization problem than the quantification problem. So when there are multiple tasks that have different level of difficulty, if we just simply put them in parallel so we can simultaneously performing those tasks, we end up having a biased training that's dominated by the easier task. So our learning method will put a lot of effort trying to do a good job of the easier task, even if we have to sacrifice some accuracy for this harder to learn task. Right? And even that happens even if the harder to learn task may be more important or equally important. So to address this bias issues, we came up with two different solutions. The first one is we can formulate the feature hierarchy to reallocate the learning resources or computational resources for harder to learn tasks. So this is between the different tasks, looking at how the data distribution shift is changing for one task versus the other task, even within the same bridge. But then there's also between bridge data shift. So how your data distribution changes when you move from bridge 1 to bridge 2 can be different depending on which task you're looking at. So in our second solution, we introduced a new optimization strategy that will prioritize the tasks that have more mismatched data distribution, meaning which is harder to classify problem. So how do we actually realize this is, so here's the original or the previous architecture we built based on the unsupervised domain adaptation and the multitask learning. And now we're going to introduce a second layer of features for the harder to learn task. So in this case, it's a severity predictor or severity classifier that had a harder to learn task. So in front of or before performing the damage quantification, we extracted a second layer of feature, the task specific feature. And of course, we want this feature to be also domain invariant. So we included a task specific domain classifier to this feature to make sure that it's still not be able to classify which bridge the data is coming from. So this is the hierarchical feature extractor framework. Okay. So now this is the final framework we developed, and it's quite complicated now. So to find out the right parameter for this model, or to come up with a solution to describe this model, we first derived the generalization risk bound. So I won't go into the details of the math due to the time limitation, but I'll just cover the insights behind this derivation. So we're basically trying to find the upper bound for the prediction error for classifying or diagnosing damage in bridge 2 if we build a model based on the data collected from bridge number 1. So it's upper bounded by the summation of 3 parts. The first part is the prediction error for bridge number 1, plus the difference between the source and target domain, meaning that the differences in data distribution between bridge number 1 and bridge number 2. And then the last part is the theoretical or ideal hypothesis error for classification problem in bridge number 1 and bridge number 2. So once we fix the problem framework or the architecture I showed in the earlier slides, the third part is actually just a fixed constant. There's nothing to change here because that's a theoretical or ideal error we can get. However, the first 2 parts can change depending on how we set the model parameter. So in order to learn what's the optimal model parameter for the architecture I showed earlier, we are going to develop an optimization problem that will minimize this upper bound, which is the summation of these 2 parts. So by optimizing or by minimizing the first part, the source domain risk, we are ensuring the task informativeness of the extracted feature. And by optimizing the second part, we are ensuring the domain invariance of the feature that we extracted. Okay. So we formulate this as an optimization problem, and once we solve that optimization problem, we can find the parameter values for the architecture that I showed in the earlier slide, and then that will be the development of the domain invariant feature extractor and the classifier. So to show how this works, how well it works, we went ahead and did a lab experimental evaluation. So as this video shows, we built a lab scale experimental setup with a small bridge and the vehicle that's driving across it with a controlled speed. So we had 2 structurally different bridges and 3 different vehicle configurations that are loaded with different sensors inside. And then for each bridge, we induce 4 different levels of damage severity and 3 different damage location. And here's the quick results. So we have 3 tasks: damage detection, localization, and quantification. And x-axis shows the different approach that we can use to perform these tasks. The last column shows the results of our approach, and the others are the baseline approach. And y-axis is the accuracy or F1 scores. So the quick conclusions are that we actually saw twice the accuracy improvement, so 100% improvement in accuracy in all tests when we compared our method performance to those that doesn't have the domain adaptation part. And the second conclusion is we had about 50% increase in accuracy in damage quantification, which was the hardest task, when we compare our method's performance with those that does not have the multitask learning or hierarchical feature extraction method. So that was a significant improvement in accuracy. And the next step was to do a field evaluation. So we collaborated with the Port Authority of Allegheny County to instrument the Pittsburgh light rail system. And the train that's shown in this picture is one of the trains that we instrumented. So we put GPS and accelerometers in these trains. We started this experiment in 2013, and since then it's been continuously collecting data. We stopped the data collection in early 2020 because of the COVID. So in case anyone's interested, we actually open source this data. So it's called the Dr. Train, or dynamic responses of the train data set. So in addition to the train vibration responses that we collected, we also included the maintenance and the inspection log from Port Authority there as a ground truth for the damaged state of the rail tracks or the train itself. Okay. Just to show you the scale of the deployment, this is a 2 km by 9 km Google map with the train trajectory drawn on top of it. So the trajectory goes through 11 different bridges in the Pittsburgh area. And the quick result is that we were able to detect some changes happening to the track with 92% accuracy. And in the Panhandle Bridge, where we conducted an experiment, I briefly talked about the experiment done between 1 a.m. and 6 a.m. earlier. So in that bridge, we had 3 different damage cases, and we're able to quantify damage with 80% accuracy in an unsupervised learning fashion. Okay. And there was one case that actually the Port Authority came to us asking for help because they found that their train kept coming back to the station with the wheels chipped. So if there's a small chip in the wheel, eventually it can grow into a crack, and that could cause a derailment. So it's a severe safety issue. So Port Authority was very keen on finding what's causing the issue so they can get rid of it, but they couldn't figure it out. So we started looking into our data set. So we got the data from a month before when the problem started happening. And we also had a data after the chipping started happening. And when we compared it, we found 5 candidate locations that's potentially causing issues to the train. And in one of the locations, so Port Authority sent out the inspector to those locations. And one of the locations, they found out that there was a metal piece that was hitting on the train when the train was passing by and causing the chipping. So they cleared it out, and after that, it was the problem was gone. So using the data set like this and the learning algorithm and the change detection methods, we can quickly figure out what may be causing the damage and save a lot of time for the government or whoever is maintaining the infrastructure system. Because otherwise, another option was to have an engineer or inspector walk on every segment of the track to visually look for or visually find what may be causing that issue. So the next step is now moving from train to the car. So we're working on making the car-based bridge monitoring system in the field. So here, this shows an example of one of the bridges in the city of San Jose. It's a 3-span concrete bridge, and we're combining the car vibration responses with the fiber optic telecommunication cables that's crossing the bridge. So it's an example of non-dedicated sensing. So any telecommunication cable contains some dark cables that they're not using for internet or telephone lines. So we are actually turning them into a vibration sensor, specifically the strain sensors. It's called the distributed acoustic sensing. And along with the car vibration sensors, accelerometer data, the DOS data will give us the strain response of the bridge as the regular traffic is happening. And this is a collaboration with my colleague in geophysics department, whose name is Professor Biondo Biondi. So we're at the beginning stage of the project, so we are making sure that the data we collected from the telecom cables are actually comparable to the accelerometer data that we typically use for bridge monitoring. And we found very promising results that the major peaks extracted from the 2 sensors are matching pretty closely. And also those most shapes are pretty similar to each other. So we're pretty confident that the telecom cables can be actually used to monitor the bridge health. Okay, so that was an example of using the vehicles as sensors. And just to show you the generalizability of the structures as sensors idea, let me show you another project where we use the building structure as a sensor. So building vibration sensing is a pretty familiar topic to many structural engineers and civil engineers because building vibration contains a lot of information about the dynamic characteristics of the building structure and the input excitation. So a lot of structural health monitoring and earthquake engineering application has been utilizing the building vibration data for damage diagnosis, prognosis, developing fragility functions, or doing serviceability analysis. But then, my group was also initially doing structural health monitoring using building vibration. So we set up the sensing system and campus building to collect data. We will usually do it late at night or during the weekend because that's when it's usually quiet, less activities happening, less interference to the people while we're doing the data collection. And it's a more quiet time. But then when we're collecting the building vibration data, we had a student who actually was staying late there in his office, and he came out of his office to go to the bathroom. So I told my student, that I had a PhD student there, to stop the experiment until he come back out, because there may be some noise and it may not be usable later. The data may not be comparable, so not usable later. So we're waiting, and a little later he came out. I asked the student to restart the data collection, and she came to me and said, "Hey, Young, you know what? He actually didn't wash his hands after going to the bathroom." So I was surprised. How did you know? You were sitting here with me while he was in the bathroom. And she said, "Oh, I was looking at my computer screen to look at the data that's coming up. And she saw small impulses whenever he was walking. And then he opened the door, went inside, she saw smaller impulses. And then it was quiet for a while. And then he flushed the toilet. There was a large noise from flushing. And then she started seeing small impulse. Open the door, the student came out, and there was a larger impulse when he was walking by. So I found the individual impulses are his footsteps, and then there was a signal for toilet flushing, but there was no time for him to stop to wash his hand, nor any signal that was indicating the water system running for the sink. So we were all very surprised, like, oh, that's interesting. It's actually the building vibration data contains a lot more information than just structural health. So we went ahead and did a more experiment to focus on how well the building vibration data can collect the human information. So looking at footstep-induced floor vibration, we can find a lot of information about the occupants and their activities and even their health status. So we're sensing through the structure, so it has several benefits compared to other human monitoring systems. Namely, we're passively or indirectly sensing the human activity through structure, so there's no need to carry a device or wearables for the human occupant. It's very non-intrusive and minimal interference, causing minimal interference to the occupant while we are monitoring their activities or health. And there's much less perceived privacy concern compared to sensors like cameras or microphones. And sensing through structure, it gave us a very big sensing range. We found that for a single sensor in an open area, we were able to get about 10-meter radius, which is about 20-meter diameter sensing range for a single sensor. Here's an example of the signal we can collect. So x-axis is time, y-axis shows the vertical velocity of the floor as a person is walking by. So you see smaller impulses. Individual impulses are the footsteps, and you see the amplitude is increasing as the person is approaching the sensor, and then it's gradually decreasing as the person passes by the sensor and move away from it. So if you spread out the sensor, here we use the sensor called the geophone that's measuring the velocity of the floor. and a person walks in and have a footstep, it will create a wave that will propagate and hits the sensor at different time with different waveform. And by combining these together, we were able to find out who you are, where you are, what kind of activities you're doing, and even your health status or your cognitive status. So this is a video showing a person walking by and the data we're collecting. So top plot is the time domain signal. Bottom figure is the corresponding frequency spectrum. And red boxes means that our system has detected an impulse induced by a person. So when we detect an impulse, deciding whether it's a human footstep versus other non-footstep events like door closing or dropping an object or dragging a chair, it is a straightforward classification problem. And once we detect human footstep, the first thing we tried is identifying who that person is. There's a study. There are medical studies saying each person has a unique gait pattern because our bone structure is different, muscles different, our brains wired differently. So when we walk, we have a different walking pattern. So we have here, I have two examples. So on the left-hand side is a PhD student, Carlos, a former PhD student, Carlos. And on the right-hand side is a master's student, Ning Ning. Carlos he was very busy, he had a lot of deadlines, and he has also he tends to be always in a hurry. So you see that the way he walks is very forward motion, whereas Ning Ning, on the other hand, had a very relaxed personality. And this was also after the final exam, and there was nothing to worry about. So the way she walks, if you look at it, her center of gravity is kept pretty back compared to Carlos. And that created also the differences in how their foot hits the floor. Carlos had much smaller angle, where Ning Ning had a larger angle with more stumping kind of action. So that created the differences in the vibration data we collected from the floor. You see that Carlos on the top row has a much slower decaying signal, whereas Ning Ning in the bottom row has a much sharp decline in the amplitude. So we extracted all these as a features and put them into classifier to classify who's who. So we evaluated with 10 different people and got the 90% accuracy for individual footstep-based classification and up to 99% accuracy for trace level classification, meaning if you have consecutive footsteps, we combine them together and put them together into a classifier to identify who is walking there. So it was a pretty good accuracy, 99% accuracy. But then we found a challenge. When we move from one location to another location in the building, our accuracy dropped to about 20%. And it wasn't just about the identification problem. Our detection of footstep versus all the other impulses, which used to be 99% accuracy, dropped down to, it was a 63% accuracy. So we started looking into this problem more. What happens when we move to a different structure? Now you see a similar theme that we saw in the previous example with the vehicle-based bridge health monitoring. When we move from one structure to another structure, the data distribution will change because the vibration data is coming from the structure itself. So the naive solution is we need to collect data and calibrate and retrain the model in every single structure. But instead of doing that, in order to reduce the data requirement, our solution is to transfer the model or extract the feature and transfer it to a new space so that we can reduce the structure effect. So basically, again, when we have a set of source structure with available label data, And we developed the model, but we're going to transfer this model so that this model is usable also for the target structures that doesn't have any label data. So let me just quickly go through the methods. So when we have two data distribution that's coming from human footstep and all the others, but there's a differences due to the different excitation. So that's called the excitation effect. But both of them belong to the same structure, the source structure. But if we move to a second location or another structure, that's going to have a different data distribution because it's a different structure. So the distance between two data distribution, we'll call it structure effect. And now we want to find a new feature space where we are transferring this both data distribution to, so that will minimize this structure effect or the distance between the two blocks, the orange one and the gray one. So now the question boils down to how can we find this transfer function or the projection matrix W? The difference between this transfer and the previous transfer for the vehicle case is that there we're talking about the damage detection, meaning there can be some nonlinear transformation of the feature happening. Whereas here, when humans are walking on the structure, there's no damage. Everything is a linear relationship. So now the W matrix is a linear coefficient for this feature transfer. So we can formulate it as an optimization to find the W. So again, I won't go into the mathematical detail here, but we're basically looking for W that will minimize the sum of the structure effect, the distance between the two data distribution, plus we have a regularization term to make it robust to the noise effect, and then the distribution shape preserving term to make sure that we don't converge into a trivial solution, meaning if you multiply everything by 0, then all the data will be on top of each other. But that's not the solution we're looking for. So we have shape preserving term. And then, of course, we have label information to make sure that different classes are still separable. By solving this equation or optimization problem, we can find the transfer function W or projection matrix W. And using the projection matrix, we can transfer the feature from one domain to another domain. So our classification model is usable even if you move from one structure to another structure. So we collected data from 3 different structures or buildings and applied our method to see the performance. The green bar here is the outcome of our approach, which got up to 99% accuracy, which is a huge improvement compared to other conventional methods that doesn't incorporate the model transfer. So blue bars and the red bars are the conventional method that doesn't include the model transfer. So in summary, using buildings as sensors, we were able to identify people with up to 99% accuracy. We were also able to localize individual person with 20 centimeter accuracy, and we made it work even when there are multiple people walking at the same time. And more recently, we've been working on characterizing different types of activities and people's gait pattern with different health status. And for that, we had up to 95% accuracy for differentiating the gait pattern coming from healthy versus the non-healthy subjects. Okay. So putting it all together, we actually developed a live demo. Looking similar to this magical map in the movie Harry Potter. So in Harry Potter, they have a map called the Marauders map, which shows the little footsteps of everyone that's in the castle. So similar to that, let me see if the video works. Here's the geophone sensor that we use. And when we put it on the floor, and here's one of our PhD student walking, you can see that on the map, there's a small footstep that's moving as the person is walking. And now he's gonna walk forward and then stop and turn around, change the direction. And you see this footstep is actually moving back. Okay. So the system can actually locate individual footsteps and track it and find your location in the building. So by putting all this together, one real world deployment we did is monitoring the patients who have muscular dystrophy. So that's a neuromuscular disease, which one of the early symptoms of this disease is the gait pattern change. So we're working with the Nationwide Children's Hospital to monitor the Amish community, the boys in Amish community who has this muscular dystrophy disease. So we are basically understanding the patient's disease status, like through the gait pattern, like how well they can walk, what's the walking speed, do they have the heel toe motion that typical or normal walking pattern has, what's a left-right balance, what's a ground reaction force when they're stepping, and so on. And it can provide around-the-clock health status of the patient in addition to their monthly visit to the doctor to get the clinical data collection. Just a quick result. It looks like we're running out of time. So using more symptom-based or traditional features, we were able to get up to 86% of detecting whether the gait pattern belongs to the patient or the normal subject, healthy subject. And using our approach with the structural effect reduction method, we were able to get up to 96% accuracy. And we are further expanding this project to include different kind of application. One is animal health monitoring. So by putting these sensors on the ground in the animal farm, we can also track animals' activity levels, find out different types of activities like feeding, sleeping, and nursing, and so on. So this project, our goal is to reduce the piglet mortality rate by investigating how well the mother pig is taking care of the little piglets. And we're working with the eldercare to help elderly monitor their gait patterns and predict the fall hazard. So there's a lot of technology that can detect the fall, but our goal is to predict whether the fall may happen in the next few steps or not. Because if you detect the fall, it's already too late. So we want to prevent the falls happening. And finally, we're also doing human activity monitoring like hand washing or cooking or vacuuming and so on. Okay, so that's it for today. I would like to, before I finish, I would like to thank all my students who has been working on this project, as well as our deployment partners and funders. It would have been impossible to do all this project without their help. So thanks, everyone.
Thank you very much. Fascinating talk. I think we can invite one or two questions. Anybody wants to ask?
Yeah, I'll ask a question. Thank you very much for your presentation. It was very interesting. So for the monitoring using vehicle frames, did you find that other vehicles on the road impacted your measurements? And if so, how many times did you need to take that vehicle over a given bridge to get a characteristic signal?
Mm-hmm. That's a very good question, because when there are multiple vehicles running, that will definitely impact how the bridge will vibrate, which will impact how the vehicle is going to vibrate. So we are, so here the goal is we want to get a distribution of the data when all these uncertainties about different vehicle distribution is happening. And as you mentioned, we are we do a multiple runs of the cars running. So all the results we got here is about combining about 20-30 samples of data. So 20-30 samples of the vehicle passes happening. Of course, if we have more data, that will include also different temperature conditions or the wind speed. So it can incorporate more uncertainties in there, so it can develop more robust models. But then it will take longer time to develop that model. So there's always a trade-off. There's no one perfect solution. But that's a very important point when designing the model.
Thank you. I have one follow on. For the distributed acoustic sensing measurements of your bridge, I noticed there were some higher frequency components in higher frequencies. Do you think that the conduit that the telecommunications cables are in, they're usually hanging off of bridges. Do you think that that telecommunications conduit's dynamics impacted your dynamic measurements?
Yeah, definitely. So it will be part of the vibration. So if it's hanging, depending on how it's attached, if it's just like having a direct contact, or if it has a rod coming down and have it hanging there, it will have a pendulum kind of effect. So it will definitely impact the measurement done by us. And the high frequency that you see in the signal, whether it's exactly due to that or other impact, that will need a further investigation. So I don't have an exact answer for it, but whether that particular peak is that or not, it is definitely true that how its attachment will impact impact the data we're collecting. And another thing we found is actually so we actually have measurement at every meter, but in every location, the sensitivity is a little different because the attachment is different, and also because of how the fiber is built, sensitivity is different. So we are currently working on how to calibrate for different sensitivity level at different locations.
What was the gauge length of that acquisition?
The gauge length is oh, you mean the 1 meter?
No, the gauge length, the DAS measurement gauge length. So you're measuring strain over a length. What length, do you know?
I don't have the number on top of my head. I think it was in the order of like a 10 kilometer or so.
Oh, thank you.
It was coming from the San Jose City Hall.
Yeah.
And then it was passing by, and it also goes to the overpassing 101. But yeah, I think in our discussion it was like about a 10 kilometer, but I can double check.
Just curious. Okay, thanks.
Maybe you can discuss later on. Peter works on DAS as well. So
oh, nice. Great.
Any other questions from my colleagues?
Yeah, I just have one quick question. I'm wondering about how do you label the data? So my understanding, so you have a bridge which you have identified the damage, and then you have one dimension time series data. So is that one time series is one label, or you labels for each instance of that time series?
We induce damage. So inducing has a different meaning. So in left scale data, we actually cut the parts or loosen the bolt. So we create one damage scenario, or in the field experiment, we will load the bridge in a different way. And then we have the vehicle running. So entire time series correspond to one damage level. Yeah.
Okay, thanks.
Yeah, I think thanks a lot for your talk. I think it sort of excited many people, showed an interest. What can we use your technique for other applications? And I see some of the comment I received is that how can you use it for buried infrastructure? So that is my colleague from water industry asking that. So can the vehicles try to detect what's going on, not the bridge, but then the pipeline underneath?
Yeah, that's definitely one of the topics we're looking into, whether we can do the underground structure. Yeah. We're currently talking to the facility and on campus, on Stanford campus, to see if we can detect the tunnel underground using the vehicle vibration and combining with the DAS data as well.
And you start to detect people's feeling and emotions. So maybe you can start to detect how people drive safely or not safely and that sort of thing. So there's a lot of imagination we can do. Well, thank you very much. I think Bernie has showed up, meaning that we should stop. So thank you very much for your elegant and nice talk. And it was really enjoyable to listen to.
Yeah, thank you for inviting me. It was a great pleasure to see you all. And I hope to see you in person soon as well.
Thank you, Haeyoung.
Thank you.
Thank you very much for joining this particular seminar. I'm just going to share one slide that's happening in 2 weeks' time. If I share my screen, if I can do that. Do you see my screen?
Yes, we do.
Oh, yeah, yeah. So we're having an upcoming seminar on April 22nd, Advances in Computer Vision-Based Civil Infrastructure Inspection and Monitoring by Professor Bill Spencer from University of Illinois and Urbana-Champaign. So please join this particular seminar as well. This is the final seminar from our ITS seminar series on smart infrastructure. Thank you very much for joining today.